Hello, welcome to the second video in Momentum, part 2. I've just recorded part 1, so my voice is a bit croaky because I haven't stopped talking for ages. But in part 2, we're going to start to look at, initially, on impact forces. And so, impact forces uses the equation F, which is the impact force, is equal to delta mv over delta t. And just as a side note, this can be rearranged to these different types of equations. So, force is equal to F equals ma, mass times acceleration. And so from this one as well, if we have mass times acceleration is equal to delta mv over delta t, we can say that if we assume, remember, it can only be rearranged to these equations when we assume that mass is constant. Remember that. We can assume that the masses can cancel at either side, and we'll get A is equal to V minus U over T, or delta V over T. And you know that because that's just the equation for acceleration. So just keep those in mind for any questions you're doing. But impact forces. Impact force is, say you have a golf club, my very amazingly drawn golf club, and it hits a ball, where the force exerted on the ball by the golf club will be the impact force, and the ball will be moving with momentum equal to the impact force. So the force of impact, as we just said, will be equal to delta mv over delta t. Change of momentum over contact time. So contact time, that delta t is the time that the golf club is touching the ball for. So there generally be a quite small time, generally. But you know, a high contact time means these kind of things. But I'll get onto that in a second. The way we measure impact force is quite simple. Don't let hopefully I'm not overcomplicating it, but it's very simple just to understand. It's just this equation, and it's quite easy to understand. The only thing I suppose you have to understand is that the time is going to be the contact time, not like swing time and stuff, you know. And so the way we measure this is if we have an object and we throw something at it, it has a force sensor on it, which will measure the force exerted on this sensor. And we'll have like we were talking about in the last video, the force time graphs here. The force exerted on it, so it may hit this object, start off with a small force, but and it will like, ooh, the big force, and then you know it'll go down as it's coming back away from the bouncing off of the object. So it hits it, and this will be connected to a computer, which will plot it electronically because we won't be able to measure the contact time. It'll be such a small amount of time that we won't be able to measure it accurately. So it'll be computationally drawn a graph. So that's just how you measure it. Quite simple. This is going to be quite a short video, by the way, because there's not too much to know about momentum anymore. And so the way this is applicable is in airbags in cars, for example, and crumple zones. So safety. This is a very important equation when you're trying to maximize the safety of something. Because if you've got a very massive, well, I'll get onto it. So an increased impact time, you can increase the impact time, so the contact time basically, to decrease the acceleration and thus force. So let's say you want to make an airbag. Airbags, they're useful because they come out really quickly, and then you bang into them, and so it's like your face is moving really fast forward, and then it'll decrease the amount of time for your face to hit the steering wheel. And so if this delta t here is greater, so let's say that it's now 10 times greater than it would be if you had no airbag. So if no airbag, it'd be poof right into the head counter or whatever it's called. I don't drive, so if it were 10 times greater due to this airbag being here and you slowly deflating into the steering wheel or wherever you're going to be hitting, then if you're dividing something by 10, it's going to be, the momentum's going to be 10 times less. You know, it's going to be a lot less, and so the force will be smaller. The impact force that you hit that counter or with steering wheel at will be a lot smaller. So that's a good principle a good practical situation to understand how impact force equation is quite useful. Just remember that in this circumstance, this is impact force that's acting, and this time here is the contact time. So, This is again, you can talk about impact forces and rebound impacts. So one thing I haven't really talked about all that much but momentum is a vector force. So a vector has a vector, so it has a direction. So you can have positive momentum, say moving to the right. Yes, the right, my left and right. Um, and if it were moving back on itself, so to the left, it will have negative momentum because momentum's a vector. And so in this way, if we're trying to figure out the impact force on the wall here, then we can use this equation, force is equal to minus mv minus mu over delta t. Okay, so this minus mv minus mu, this is the velocity after it's hit the wall, and the u is the velocity before it's hit the wall. We can assume mass is constant usually, but it's minus mv minus mu because as you can see here, it's minus mv because it's moving in the opposite direction. Momentum is a vector, and so it's going to be a minus value, negative momentum. Okay, and so maybe it's easier if you understand, if you remember from the first video that mv minus mu is going to be the change in momentum. But if that final momentum is negative value, it's going to be minus mv minus mu, which will be the change in momentum, and because this initial momentum here is going to be positive. I think I've explained that all right, so if I haven't, just make sure to comment and I'll try and explain it better. Over delta t, so the contact time. Because remember, we're looking for the impact force, so we're looking for the contact time on the wall here. Just as a little side note down here, I've put if in a head-on collision the two objects stop, so if two objects hit together and they stop, it means that the momentum of both the objects will be equal, because if they're moving in towards each other, the vector of the momentum is going to be equal and opposite, well, opposite vectors. So one's going to be positive, one's going to be negative. As they hit together, if the momentums of both of them is the same, then it's going to be an equal and opposite reaction. They're just going to stop because they'll cancel each other out. Just as a side note. So in these two equations here, these are two equations which where speed is not lost. So you have to remember, you can only use pardon me, these equations if there's no loss of speed in the system. So, sorry, I've got a sore throat. If the force is equal, force is equal to minus 2 mu over delta t. It's the same equation as this one, remember, except we don't have a final velocity. Well, we do have a final velocity, but they're the same. So v and u in this case are the same because there's no loss of speed. The speed is constant in this case. And so we can represent v as simply u, or it could be v, but v is usually said to represent the final velocity. This is the initial velocity, and the final velocity in this case is the same as the initial velocity, so we just give it a value u. And if this were u here, so if this were minus mu, we can just say it's going to be minus 2 mu. Yeah? Because it's like minus 1 is just minus 2. Over delta t. So that's a useful little equation. You might get asked in questions maybe why this is. Now you know why it will be that, because if speed is constant, this equation applies because momentum is a vector, and you will end up with minus 2 mu. And again, if you have it's the same for this equation here. F is equal to minus mu cos theta, because I'm assuming that you've been over things like this, and if you haven't, I'm sure we'll be going over. I'm not really sure about. I haven't looked too much over the syllabus, but for A2, but I'm sure we'll be going over this horrible stuff again. So yeah, just to let you know, these two equations are handy equations to know, because if there's no loss of speed, speed will be constant. So there you go. I'm not sure. I could go into more detail on them, but I'll be going into different topics, and I want to stick to momentum. So just remember those two equations and try and understand them. Of course, I mean, I'm assuming you can understand them because they work because velocity is constant in this case. But moving on. Elastic and inelastic collisions. I said I'd go over elastic and inelastic collisions. So an elastic collision, which we were talking about in the first video, is when there's no loss of kinetic energy in an impact. So there's no loss to the surroundings of energy in an impact. Two objects collide, no energy is lost to sound or heat, or so the kinetic energy stays the same. And these will be called elastic objects. In an inelastic collision, is when there is a loss of energy. So this is more practical. This is usually what happens when energy is lost to the surroundings in an impact. And you have two different types of these inelastic collisions. You have totally inelastic collisions, which is the one in the last video we talked about with that question where the two wagons coupled together. So this is when colliding objects stick together because there is a total loss of energy in the system. And partially inelastic collision is when colliding objects move apart, so it's only partially inelastic. It's slightly elastic collision. Just to help you understand that, elastic collisions are objects would fly apart with no loss of energy. So they would fly apart they would bounce off each other with the same amount of kinetic energy they were coming at each other. So kind of like in this example, if you imagine it's bouncing off the duplicate of itself here, it would be boom, boom, both would be U because it's constant. So this is the kind of, this would be an elastic collision here. Okay, and I've put this here, this little diagram, because if you're ever asked to measure how, the loss of energy in a system or something, you can give this kind of example. If this blue here is a ruler, so you're measuring the height, and you will drop a ball from the height, the top of the ruler, it comes down, and you can measure the energy it has as it comes down with the equation energy is equal to mgh. So the mass times the gravitational field strength. So in this case, it would be 9.81 if you're on Earth, times by the height. Height is a capital H here because we have two equations that have height in it. So just capital H, and so then you'll know the energy the potential energy it has at the top there. So that's the total energy it has before the, say, collision here. And when it bounces back up, it'll bounce up to a lower height, unless it's an elastic collision. Otherwise, it bounces right back up to where it began, and you'd have like perpetual motion. But it's the energy it has when it goes up will be equal to E equals mgh. Again, the same equation. Energy is equal to mass times g times the height. So this would generally, in inelastic, well, it'll always be in inelastic collisions, this will be lower than this initial one. So its initial energy is going to be, its final energy is going to be lower than its initial energy. So you know it's an inelastic collision because energy has been lost, and you can do the change in these energies to find, so the range of them to find the loss of energy. Okay, and so that's it. It's quite easy, that, isn't it? E.g. It's an example, a practical example, is the excitation of gas particles. I'm sure you've been over, I won't go into what it is, but if you know what it is, excitation of gas particles. When gas particles are excited, it's an inelastic collision because the particles bounce off one another, and they will be bouncing off with less energy because some of the energy has been lost to the surroundings, so their kinetic energy afterwards would be lower. Moving on again. We almost finished this. This is a quick video. So explosions. Explosion is another part in the momentum topic. It's not exciting as it sounds, unfortunately. I got really excited when I saw explosions, then found out it's just some momentum stuff we've already really been over, to be honest. But it's nice to understanding explosions is nice to sum things up for you. So if you have two objects and you have this cart and this cart, imagine they haven't sprung apart yet, and it's got a compressed string with a lot of potential elastic energy stored inside this spring. When the spring is released, we'll call it an explosion. The same is true if it were like a stick of dynamite on the back here or something, and it would go boom and blow up. Okay. Before the spring is released, these two objects are stationary, so they have a velocity of 0, and so you can say that the momentum of the system is going to be equal to 0. So the total momentum before the explosion is equal to 0. And due to the principle of conservation of momentum, momentum after the explosion is also going to have to be equal to 0. So initial momentum is equal to 0. Momentum after the explosion is going to be the momentum of the first object plus the momentum of the second object. And remember earlier on we went over the vector, that momentum is a vector. And so momentum will be conserved, so P1 plus P2 will have to be equal to 0. Right? So this will have a momentum, say, of 5. This one will have a momentum of -5 because momentum is a vector. They're moving apart, and so the momentum will be opposite. So mb vb, so this is the momentum of the mass of the object B times by the velocity of the object B will be equal to minus ma, object A, times va. So that's the same as this one, just a bit rearranged. So P1 is equal to minus P2. So I'm sure you can understand that. It's the principle of conservation momentum. It's handy to know though, because it's nice little summary. I like how they included this at the end because it sums things up quite nicely. So these two objects, if there's an explosion between them, they'll move apart with the same momentum. Because momentum will be conserved, momentum is going to be 0. And here's a nice, I like this example because, anyway, it doesn't matter if I like it. So you have a big atom here, so alpha to k, so it's got over 82, I can't remember, alpha to k is 8 protons, I think, 82 protons, in this atom. And so it's going to go over through alpha to k. So it spits out a helium. Yes, helium. I'm sure it's helium. This helium's got a much lower mass compared to this atom here. But because it's an explosion, it's kind of like well, it is an explosion when this helium spits out because it's got like potential energy and it goes poof and spits it out as the energy is released. This helium, although, right, okay, let me gather my thoughts here. The principle of conservation of momentum says that the momentum before has to be as same as after. So if we assume this atom is stationary before the alpha to k, when it spits out this helium, which has a much lower mass, it's going to move away from this atom here with a much higher velocity. Okay? And this one will move away slightly, but its velocity will be almost negligible in comparison because it's such a massive thing compared to this. The mass is so much, the ratio of masses is going to be very big. So if we say that, yeah, I mean, I kind of want to finish up the video, but hopefully you can understand that. If you don't understand that, I think this is a really good example to understand. So if you don't understand that, make sure to comment, and I'll make sure to explain it a lot more fuller. But that's a good example. So get your head around that one, and that's a nice thing to think about when you think of momentum questions. I like that one anyway. It's also you can also apply this one nicely to like Newton's laws of motion, like the third law, equal and opposite reactions and things. But otherwise, I think that we should finish the video there. Thanks for watching. Hopefully, this is the last video on momentum, by the way. So this is the entire momentum topic. If I haven't covered anything in enough detail, or you think I've got, even if you think I've got something wrong as well, because I'm learning this as well as you are. But if you think I've got something wrong, make sure to comment, and I'll try and I'll correct it in the video and things. But thanks for watching, and hope it helps. Have a good one. Make sure to watch the other videos I've got in chemistry and DT and stuff. So, thanks. Bye. Oh shit. Bye.